April 19 this year, opening ceremony of Fukushima Renewable Energy Institute, FRIA, and Future PV Innovation was held. We had a large number of visitors, including VIPs, Deputy Director General next, President AIST and the former President AIST, and the Chairman K. Dunn and so on. So they are looking very nice Nakajima Sensei's large fantasies. Okay. And we had discussions with those visitors. I briefly talk about our recent activity. I just show 3 view graphs about this. First one is super high quality silicon crystal growth. Professor Nakajima is conducting new growth techniques named non-contact crucible method. This is Professor Nakajima's original idea. We can expect to reduce dislocation density, and also we can expect to improve the magnetic carrier lifetime. And up to now, we have achieved a carrier lifetime of 3.2 milliseconds. This data was measured by Professor Anthony Brunasisi, MIT, so thank you for your kind measurement. And this shows how we prepare the silicon wire and wall structures. I classified our technique into 2 parts, etching technique and growth techniques. And etching technique is divided into several parts, but lithography technique, so-called top-down technique, and metal-assisted etching. And up to now, Dr. Ichikawa achieved minimum wall thickness of 1.5 nanometer. More detail will be reported later. And also for silicon nanowire films, we succeeded to measure. We demonstrated for the first time of carrier lifetime of wire structure, 10 microseconds. And also we prepared amorphous silicon and SiO2 superlative structures, and then after annealed, we observed clear shift of photoluminescence peak, and we achieved estimated energy band gap of 1.5 electron volt already. And also we are trying bottom-up techniques, so-called growth technique. We are using a VLS growth method, vapor, liquid, solid growth. But those are still a primitive stage. So later, team leader or by posters, we show more detail. Here is Team 3's achievement regarding solar cell performance. In group 3-1, we are preparing a high efficiency silicon bottom cell, and our point is to use amorphous SiO as a passivation layer of silicon solar cell. And up to now, we achieved a magnetic carrier lifetime 10 milliseconds and open circuit voltage 0.738 and efficiency 20.1%. And also we are developing processes for preparing wire solar cells, and this is preliminary results, but 11% for microwire solar cell. And for nanowall monolithic tandem solar cell, Dr. Ichikawa's group are trying to develop also processes, and by using monolithic tandem structures, roughly 10% have been achieved already. And for amorphous silicon wire solar cell, this solar cell can be used as top cell. Already 10.7% has been achieved. And also we have coupling technique, confined technique, so on. This is a summary of photographs we achieved up to now. Okay. Anyway, from this April, formally, the activity in Korean City just started, and 2nd April we had a meeting to have a safety training. Anyway, we try our best making a Fukushima Research Center base for transmission information of innovative solar cells to the world. Oh, thank you for your kind attention.
Thank you for your presentation, Professor Konagai. Now this paper is now open for questions and comments. We have 5 minutes for discussion. Are there any questions or comments? please. Please give your name and affiliation before your questions and comments. And use the microphone, please.
I'm wondering there are two important factors to improve the solar cell. One is the quality, and second one is cost.
Yes.
And so, what do you think about the cost?
Okay. Today, I have no time to talk about the cost of our wire solar cell, but our final target is to use a low concentrating system to reduce electricity cost. So probably 10,000 is just okay for us. So from this year, we just start this program, low concentrating system. We set up those systems here in Koreama. Yeah. This is just for reducing electricity cost. Of course, we use a so sophisticated device structure. So in the initial stage of development, of course, manufacturing cost is very high. So that's why we use those techniques to reduce electricity cost.
Is it okay? Is there any other questions and comments? Anyone have any questions? Professor Konagai, do you have anything to add on this topic?
そうね。それは困りましたね。
Please,
Okay.
Professor Werner will bring the microphone.
You mentioned in your transparency number 24, you had two results on
24?
yes.
Just one, 24. This one.
This one, yes.
Yeah.
You mentioned two results on. No, that you had solid results already on quantum. Yes, 11% and 9%. Now,
Just the beginning. You know.
yeah, I know.
Very
These are
stage.
wonderful numbers. I don't want to criticize that, but do you have any experimental proof that these salts are based? The function of the salts is based on quantization?
No, not present. No, we need to reduce the thickness to several nanometer. But we are now trying. We are now trying to develop processes for preparing.
Yeah, but for example, the 1.5 nanometer salts.
This is just a demonstration of thinning of wire thickness, and 10% is just the process development.
Is it a crystalline silicon salt, or is it a amorphous silicon salt?
This is crystal silicon. So I said just the beginning of, we need to unique processes for preparing tandem.
It's very difficult. very.
We are challenging.
Difficult.
We are challenging.
Challenging.
Yes.
Thank you very much. I'm sorry, but we're out of time, so please continue your discussion in the break. Thank you again for your presentation, Professor Konagai.